Hello. If you are hearing this, then you have made it to the end of the day. Whatever filled those hours, the meetings, the decisions, the small frustrations, the long silences, all of it has led you here, to this moment, to this stillness. You do not need to hold any of it anymore. I want you to let your shoulders lower, just slightly, not forced, just allowed. Let the weight of your head settle more fully into whatever's behind it. The pillow, the cushion, the gentle darkness. Tonight, we are going somewhere together. Somewhere so vast, so calm, so deeply, profoundly empty that the noise of everyday life simply cannot follow us there. We are going to the Boötes Void. Say that name with me, softly, in your mind. Boötes, the Boötes Void. It is a place in the universe unlike almost any other. A region of space so large, so silent, so remarkably, beautifully empty that astronomers simply call the great nothing. And tonight, we're going to drift through it together, slowly. There is no rush. There is nothing to understand fully, nothing to remember, nothing to solve. If your eyes are still open, let them soften. Let the edges of things blur a little. Let the room around you grow dim and distant. And if they're already closed, that is wonderful. That is exactly right. Let us begin. The universe is not filled with stars. That is the first thing, the quiet truth that most people do not carry with them. When we imagine space, we imagine lights. We imagine galaxies and nebulae and the warm glow of distant suns. We imagine fullness. But the universe is mostly empty. Overwhelmingly, vastly, almost incomprehensibly empty. The stars and galaxies we see, all of them, the entire visible, luminous, breathing cosmos, they make up only a thin lacework, a network of filaments and walls and clusters, stretched across the great dark like the surface of soap bubbles held together in a bowl. And the insides of those bubbles, nothing, or nearly nothing. Immense hollows of space, called voids, where the usual rules of crowding and collision and gravitational drama simply do not apply. These voids are not exceptions. They are the rule. They make up approximately 80% of the volume of everything that exists. Let that settle very gently. 80% of the universe is essentially this quiet, slow, hollow, patient, and the largest of these hollows that we have found, one of the most extraordinarily empty places in the observable universe, is the Boötes Void. It sits far away from us, 700 million light years away, so far that the light reaching us from its edge left home before complex animals existed on Earth, before the first fish, before the first forests. And yet, in some profound and peaceful way, it belongs to the same universe as the room you are lying in right now. It is part of the same fabric, the same slow, dark, magnificent whole. Tonight, we will spend time there, fact by fact, like stepping stones across still water. There is no test at the end. There is nothing to retain. You may fall asleep at any moment, and you will have missed nothing of importance. Every fact stands alone like a star, isolated, complete, gently luminous. Here we go, into the nothing. The Boötes Void was discovered in 1981. An astronomer named Robert Kirshner was doing something that sounds almost meditative when you say it slowly, mapping the large-scale structure of the universe. He and his colleagues were conducting what is called a galactic redshift survey. They were pointing their instruments at patches of the sky and measuring very carefully how fast distant galaxies were moving away from us. From that speed, they could infer distance. And from distance, they could begin to sketch the shape of the cosmos, not just what is out there, but where. It is patient, meticulous work, the kind of science that unfolds over years, not days, the kind the slow science movement might recognize as its own. And somewhere in that careful mapping, in all those measurements and charts and quiet late nights of the telescope, Robert Kirshner noticed something deeply strange. A place where the galaxies simply stopped. Not a gap, not a small absence. A vast, alarming, beautiful emptiness that had no right to be that large. He had found the great nothing. It sits in the constellation Boötes. Boötes, pronounced Boötes, is a constellation that has watched over the northern sky for thousands of years. Its name comes from the ancient Greek for herdsman or plowman, a figure striding across the heavens, guiding the stars of the Great Bear around the celestial pole. Boötes is not particularly dramatic. It does not have the sharp geometry of Orion or the famous story of Scorpius. It is quieter than those, more patient, a wanderer. Its brightest star, Arcturus, is one of the most luminous in the night sky, a warm amber star that ancient sailors used for navigation, a reliable presence, a steady light. And somewhere beyond Arcturus, far beyond even the faintest stars visible to any naked eye, at a precise location near right ascension 14 hours and 50 minutes, declination 46 degrees north. There it is, the void, hidden behind a familiar sky, patient, waiting, silent. It lies approximately 700 million light years from Earth. 700 million light years. Let us stay with that number for a moment. Let it wash over you without any pressure to comprehend it. Numbers of this scale are not meant to be grasped. They are meant to be felt dimly, the way you feel the depth of the ocean from the shore. A light year is the distance light travels in 1 year, nearly 10 trillion kilometers. Light moving at nearly 300,000 kilometers per second for an entire year without stopping. Now hold that single year of light travel in mind and multiply it by 700 million. The light reaching our telescopes from the Boötes Void today left its source when the Earth was young, when life here was still simple, long before the first vertebrates, long before the first forest breathed oxygen into the sky, long before any eye existed to look upward and wonder. That ancient light, patient and unhurried, has been traveling ever since. And now quietly it arrives here, and we look back. It spans a diameter of roughly 330 million light years. 330 million light years from one wall to the other. Astronomers give it a radius of 62 megaparsecs, which is simply another way of expressing the same staggering distance. A megaparsec is about 3.25 million light years, 62 of those. Because of this, the void qualifies as what cosmologists call a supervoid, one of the largest known structures in the entire observable universe. To cross it at the speed of light, faster than anything can travel, would take 330 million years. If you had set out across it at the moment complex life began on Earth, moving at the speed of light, you would not be halfway through yet. There is something deeply, almost comically humbling about that thought. All of human history, all of civilization, every war and song and poem and sleep and waking, the entire arc of our species, a blink inside the crossing of a single empty place in space. And the void does not notice. It simply is. The Boötes Void represents approximately 0.27% of the observable universe's diameter, a fraction of a percent. It sounds small, and yet that fraction of a percent is 330 million light years wide, the observable universe. The full sphere of everything we can in principle see stretches about 93 billion light years across. This one void, this single hollow space, occupies a measurable slice of that totality. What it tells us more than anything is something about how the universe is organized. The light and matter, the stars and galaxies, and all the drama of cosmic existence, they cluster tightly together, press into walls and filaments and superclusters, leaving behind enormous carved-out spaces, like the bubbles in bread dough. If you could bake the bread across billions of years and billions of light years, the yeast is gravity, the dough slowly rising, pressing matter outward into the crusts, and the holes left behind, those are the voids. The Boötes Void is one of the largest holes in the bread. Warm, dark, still, it is nicknamed the Great Nothing. There is a poetry in that name, if you let it land gently. The Great Nothing, not the Great Dark, not the Great Absence, not the Great Silence, though all those would apply. The Great Nothing, a name that acknowledges, with unusual directness, that some places in the universe are defined entirely by what they do not contain. In galaxy maps, the vast three-dimensional surveys astronomers create by plotting the positions of millions of galaxies, the Boötes Void appears as a dark patch, a hole in the map, surrounded on all sides by the bright clustered filaments of the cosmic web. This region simply falls away into darkness, visible, measurable, profound. There is something almost meditative about the idea that nothingness can have a name, that an absence can be studied, mapped, and understood, that the empty spaces in the universe are not failures or accidents. They are structure. They are part of the design. The Great Nothing is not a mistake. It is as much a feature of the universe as any galaxy. It is bordered by some of the largest structures in the known universe. Imagine the void as a room, a vast, quiet, dark room, and around its walls, pressing close, dense, luminous, stand the great superclusters of the cosmos. The Hercules supercluster, the Ursa Major supercluster, the mighty Shapley concentration, one of the most massive collections of galaxies in the observable universe, the Corona Borealis supercluster, the Boötes supercluster itself. These are the walls of the room, and their presence makes the void more vivid, more apparent, more complete, like silence heard between notes of music. The emptiness is sharpened by the fullness surrounding it. Because of these neighbors, the Boötes Void has one of the sharpest contrasts between underdensity and overdensity of any structure we have found. The transition from the buzzing, crowded superclusters to the silent interior of the void is dramatic. One moment, cosmically speaking, you are surrounded. The next, nothing. Just a long, slow dark, and a faint memory of a galaxy you left behind. It is roughly spherical in shape, though elongated along one axis. If you were to sculpt it from clay, slowly, deliberately, turning in your hands, it would feel like a slightly flattened sphere, round in 3 dimensions, but stretched a little, as if gently pressed from 2 sides. And through this elongated shape, there runs something unexpected and strangely beautiful. A tunnel, a narrow corridor of galaxies, threading through the center of the void like a spine through a body. Not a wall, not a cluster, a thin line, a filament, a trace of matter that somehow survived or migrated or persisted at the heart of all that emptiness. Astronomers call structures like this filaments or tubes. They are common in the cosmic web, the network of matter that weaves through space. But finding one inside a supervoid is unusual. It suggests the void is not a perfect emptiness. It is an emptiness with a spine, an absence with a memory of structure. Even in the great nothing, something remains. Galaxies inside the void do not scatter evenly. They cluster in a tube-shaped region through its center. If you expected the inside of such a vast emptiness to be perfectly uniform, a featureless dark, the Boötes Void would gently correct you. The galaxies that do exist inside it are not distributed randomly throughout the space. They have arranged themselves over billions of years of slow gravitational nudging into a recognizable shape, a long, narrow tube threading through the void like a river through a desert. Think of it this way. Imagine a room the size of a continent, empty mostly, but through the center of that room, along its longest axis, a thin line of candles. Each candle a galaxy, separated from its nearest neighbor by millions of light years, but still, in cosmic terms, related, part of the same patient structure. This tubular arrangement tells scientists something important. Gravity, even in its weakest expressions, is not without preference. Even in the most underdense regions of the universe, matter remembers how to organize itself. It gathers, it arranges, it forms, slowly, over time, a shape. The void has a spine. The nothing has a thread of something running through it. The Boötes Void contains only about 60 galaxies. 60 in a comparable volume of space. the same 330 million light years across. The universe would typically hold around 2,000 galaxies, possibly more. Dense regions of the cosmic web hold tens of thousands. The Boötes Void holds 60. That is roughly 3% of what might be expected. A 3% occupancy. A room designed for 2,000 guests, where only 60 arrived, and they have gathered quietly at the center, near the spine. Each of those 60 galaxies is itself vast beyond imagining. Each contains billions of stars, clouds of gas and dust, probably countless planets. Life, perhaps. Stories, perhaps. But between them, between any two of those 60 lonely islands of light, there are stretches of space so wide and so empty that we have no words for the loneliness of it. And yet, somehow they persist. They endure. 60 small lights in a vast, patient dark. The average distance between galaxies inside the void reaches about 10 million light years. 10 million light years between neighbors. In our own corner of the cosmos, galaxies are comparatively close. The Andromeda Galaxy, our nearest large spiral neighbor, is about 2.5 million light years away. The local group, the small family of galaxies that includes the Milky Way, Andromeda, and a few dozen smaller companions, fits inside a sphere of roughly 10 million light years. Inside the Boötes Void, 10 million light years is the typical gap between any two galaxies, our entire galactic neighborhood. Everyone we have ever mapped and named and felt a sense of cosmic kinship with would represent the distance between two typical neighbors inside that emptiness. Imagine sitting in your home and knowing that the nearest house is not a street away or a mile away or a country away, but separated from you by the width of everything familiar, everything local, everything known. That is what it is to be a galaxy in the Boötes Void. Isolated, patient, quietly shining into the dark, with no one nearby to notice. The void lacks a central spiral galaxy cluster. Instead, sparse dwarf galaxies persist there, with very few mergers. In denser parts of the universe, galaxies are social creatures. They pull at each other. They collide slowly, magnificently, over hundreds of millions of years. They merge. They grow. Large spirals and ellipticals form from the accumulated mass of many smaller galaxies, drawn together by their mutual gravity. Inside the Boötes Void, this drama rarely unfolds. The galaxies there are too far apart, too isolated. They do not feel each other's gravity strongly enough to be drawn together. They do not merge, and so they do not grow. They remain small. They remain sparse. They remain, in a sense, as they were when they first formed, dwarf galaxies, modest in size, unhurried in evolution. No grand central cluster. No dominant spiral galaxy commanding the neighborhood. Just small, quiet inhabitants of an enormous empty room, each keeping to themselves, each evolving slowly in their own solitude. There is something almost peaceful in that image. No collisions, no disturbances, just patience. Large galaxies prefer denser zones. dwarf galaxies dominate in the void, which aligns with what scientists call hierarchical formation models. The universe builds from small to large. This is the essence of what cosmologists call hierarchical structure formation, the idea that the cosmos assembled itself in stages. First, tiny quantum fluctuations in the early universe created small ripples in the density of matter. Then gravity amplified those ripples. Small concentrations formed first. Those small concentrations merge to form larger ones. And those merge again and again over billions of years until the great superclusters and galaxy clusters we see today emerged. In dense regions, this process ran its full course. Small things became medium things, which became large things. In the Boötes Void, the process stalled early. The initial density was too low, the gravitational nudges too gentle. Small things formed, and then nothing pulled them together. They stayed small. They stayed separate. The dwarfs in the void are like seeds that were sown in thin soil, far from other seeds, in a field where the wind was too gentle to carry pollen between them. They grew. They simply never became trees. Void galaxies are mostly late-type spirals and gas-rich dwarfs, with unusual internal dynamics. Their rotational velocities can reach up to 250 kilometers per second. They spin, despite their isolation, despite the profound emptiness around them. The galaxies inside the Boötes Void are not static. They rotate, they move. Their gases orbit around their centers at speeds that, by any human measure, are extraordinary. Up to 250 kilometers every single second. They are late-type galaxies, which in astronomical terminology means they are still young in spirit, still rich with gas, still forming stars, still unsettled in the way that younger, less evolved galaxies tend to be. They have not yet used up their fuel, in part because they have had fewer encounters with other galaxies to trigger massive star-forming events. Their HI distributions, meaning the way neutral hydrogen gas spreads through them, are unusual, extended, irregular, as if the gas, with no neighbors to strip it away, has been allowed to settle wherever it pleased, spreading slowly outward into the isolation around each galaxy. They are strange, these spinning islands in the nothing, strange and active and, in their own way, alive. Many void galaxies show low surface brightness and unusual shapes, including unusually extended disks. If you could place one of the Boötes Void's galaxies next to the Milky Way, right next to it, for comparison, the difference might surprise you. The Void galaxy would be dimmer, spread thinner. Its light would not concentrate as sharply toward its center. It would appear almost eluded, a galaxy whispered rather than spoken. This is what low surface brightness means. Not dim in total light output, necessarily, but dim when you divide that light across the area it covers. Spread out, extended. Many void galaxies have grown unexpectedly large disks of stars and gas, flat, rotating structures that extend much farther from the center than a comparable galaxy in a denser environment would, without the gravitational harassment of nearby neighbors, without the tidal forces that would otherwise compress or disturb the outer edges. The disk simply spreads, like a drop of ink in still water, diffusing slowly outward in the absence of any current. Gentle, unhurried, formless at the edges, inhabitants of the void show high star formation rates relative to their isolation, possibly because they have retained large amounts of primordial gas. They are making stars. In the quiet of the great nothing, where you might expect everything to slow to a standstill, where isolation and low density might suggest stagnation, the galaxies of the Boötes Void are actively, busily, continually making new stars. And the reason may be precisely their isolation. In dense regions of the universe, galaxies interact. They collide, they pass close to each other, and those encounters stir up their gas, sometimes triggering brief, violent bursts of star formation, but also, over time, depleting the gas supply, stripping it away, using it up. The void galaxies have been left alone. Their primordial gas, the hydrogen and helium that has existed since the early universe, has never been disturbed enough to be fully consumed or expelled. It sits there patient, slowly condensing in places, slowly giving birth to new stars. In the oldest, emptiest, most isolated part of the cosmic neighborhood, new suns are being born. There's a galaxy deep inside the void named HS 1442 plus 4250. It is a blue compact dwarf, and it is actively forming stars despite its profound isolation. HS 1442 plus 4250. It has a name that sounds more like a serial number than a title, which is fitting for something so far from the centers of cosmic attention. And yet, this small galaxy is doing something remarkable. It is blue. In astronomy, blue galaxies are young and active. Their color comes from the ultraviolet light of hot, recently born stars, which glow blue before they age and cool. A blue compact dwarf is small, concentrated, and bright with the light of new stellar births. HS 1442 plus 4250 sits deep in the Boötes Void, surrounded by almost nothing. It has no large neighbors to trigger its star formation through gravitational interaction. It has no dense environment supplying fresh material. It has only its own inherited gas, its deep, patient reserve of primordial hydrogen, and it is using it, slowly, continuously making stars. In the great nothing, something new is being born, something small and blue and quietly radiant, in a region of space that the universe had almost forgotten about. Spectral studies show that void galaxies display bluer light on average, a result of less dust reddening in their sparse surroundings. Light carries information. When astronomers look at a galaxy spectrum, the full rainbow of its light, spread out from ultraviolet through infrared, they can read its history, its age, its composition, its environment. And void galaxies, when you read their light, tell a particular story. In dense regions of the universe, galaxies are surrounded by dust, not the gentle household kind, but vast clouds of microscopic carbon and silicate grains, spread through and between galaxies. This dust absorbs and scatters blue light preferentially, making galaxies appear redder than they actually are. It is a kind of cosmic fog, a reddening effect that astronomers must carefully correct for. In the void, there is less dust. The vast distances between galaxies mean fewer clouds, fewer grains, less scattering. Light travels more cleanly, more truly. The galaxies of the Boötes Void glow bluer because their light arrives unobscured. It has crossed the enormous emptiness between their stars and our telescopes without being filtered or diminished. Their true color, preserved by the nothing around them. Internal peculiar velocities inside the void stay low, under around 300 kilometers per second, reflecting weak gravitational gradients. Everything in the universe moves. Galaxies are not fixed points. They drift, pulled here and there by the gravity of their neighbors, by dark matter concentrations, by the large-scale structure of the cosmic web. Astronomers track this movement with something called peculiar velocity, the component of a galaxy's motion that cannot be explained simply by the universe's overall expansion. In dense environments, near massive galaxy clusters, for example, peculiar velocities can be enormous. Galaxies race toward each other at thousands of kilometers per second, drawn in by the gravity of great concentrations of mass. Inside the Boötes Void, the gravitational landscape is almost flat. There are no great masses to pull toward, no steep gradients, no powerful attractors. The galaxies there drift slowly, under 300 kilometers per second on average. Moving, yes, everything moves, but gently, without urgency, without the feeling of being pulled somewhere. They wander quietly through an enormous room, disturbed by almost nothing. At the edges of the void, infall velocities are twice the cosmic average, matter falling toward the surrounding superclusters. The boundary of the Boötes Void is not a quiet place. While the interior is still and undisturbed, the edges tell a different story. Here, at the thin membranes where emptiness meets density, matter is moving, and moving fast. Galaxies and gas at the void's outskirts are being pulled outward, not by anything inside the void, but by the enormous gravitational pull of the supercluster surrounding it. The Hercules supercluster, the Shapley concentration. These vast, massive structures draw matter toward them, accelerating away from the empty interior. The infall velocities at these edges are roughly twice the cosmic average. Matter is evacuating the void's margins, falling like water toward the dense walls and filaments outside. This is one of the mechanisms that keeps the void empty. As the universe ages, this process continues. Matter drains in the interior, carried outward to the bright, crowded walls. The void slowly empties itself further, growing purer over cosmic time. The great nothing is, in its own slow way, getting greater. The void's low dark matter density weakens gravitational pulls, slowing galaxy formation compared to denser regions. Dark matter is the invisible scaffolding of a universe. You cannot see it. No telescope has ever captured its image directly, and yet cosmologists are confident it exists, not because they have found it, but because of what they see when it is absent. The way galaxies rotate, the way light bends around galaxy clusters, the way large-scale structure formed it all. In denser regions of the universe, dark matter concentrations act as seeds, deep gravitational wells that pull ordinary matter, gas, dust, eventually stars, inward. These wells accelerate structure formation. They are the hidden foundations of galaxy clusters. Inside the Boötes Void, the dark matter density is low. The gravitational wells are shallow. The pulls are weak. Without those deep wells to fall into, galaxy formation proceeds slowly. There is simply not enough gravitational urgency to pull diffuse gas into tight concentrations quickly. Things form. They do form, eventually, but on longer time scales, at smaller scales, with less drama. The void is quiet partly because its invisible skeleton is sparse. Dark energy accelerates the expansion of the void faster than average space, potentially making it grow over time. Dark energy is the universe's most enigmatic force. It is not matter. It is not radiation. It does not cluster. It does not thin out as space expands. Instead, it is something intrinsic to space itself, a property of emptiness, a pressure built into the fabric of the cosmos that pushes outward, accelerating the expansion of the universe. In dense regions, inside galaxy clusters, along the walls of the cosmic web, gravity is powerful enough to partly counteract dark energy's influence locally. Structures hold together or even grow, despite the universe's overall expansion. But in the void, gravity is weak. Dark energy faces almost no resistance. The expansion of space inside the Boötes Void proceeds faster than the cosmic average. The void is not just empty. It is actively, dynamically expanding more quickly than the filled regions around it. The nothing is growing. This is a slow process, measured over cosmological timescales. But over billions of years, the void may become larger still, emptier, more complete in its nothingness. The future holds an even greater great nothing. The Boötes Void does not expand alone. All across the universe, voids are expanding simultaneously, thousands of them, each one growing slowly as the matter at their edges drains away toward the surrounding walls. Together, they form something cosmologists call the void expansion contribution, a collective pressure that adds to the universe's overall rate of growth. Because voids occupy roughly 80% of cosmic volume, their collective expansion is not a minor consideration. It shapes the large-scale dynamics of everything. When cosmologists try to measure how quickly the universe is expanding, the Hubble constant, they must account for voids. They must understand how much of the expansion they observe is driven by this collective void breathing. The universe, in a sense, is mostly lungs, and the voids of the inhale, the galaxies and filaments, the luminous, crowded structures we tend to focus on, they are the bones, important, defining, but not the dominant volume. Mostly, space is breathing, slowly, quietly, outward. Time makes the void more itself. When the Boötes Void first formed, when the early universe's density fluctuations were still gentle, still young, its boundaries were softer. The transition from interior to wall was less abrupt. The emptiness was less complete. But gravity is patient. Over billions of years, the matter at the void's edges felt the pull of the superclusters beyond. Slowly, grain by grain, galaxy by galaxy, it drained away. The interior became thinner. The walls became denser. The contrast sharpened. The boundaries of the Boötes Void today are among the sharpest density transitions in the observable universe. A steep wall from near nothing to dense clustering. The void has been refining itself for billions of years. Each year, slightly emptier. Each century, slightly more defined. The nothing becoming more precisely nothing, carved by the slow, patient work of gravity, like a negative space in a sculpture, clarified by the stone surrounding it. We live in a universe where the majority is empty, 80%. For out of every 5 cubic light years of space belongs to a void, a hollow, an underdense region where galaxies are sparse and gravity is quiet. Only 20% of the universe's volume contains the structures we tend to think of as the universe. The galaxies, the clusters, the filaments, the walls. The Boötes Void is simply one of the most spectacular representatives of that dominant 80%. When you look up at the night sky and see the Milky Way, that hazy band of light arching overhead, you are looking at one of the thinnest, most exceptional parts of the cosmos. The bright part, the crowded part, the anomaly. Most of the universe is not that. Most of the universe is the quiet, patient dark between those filaments. Most of the universe is something like the Boötes Void. We are the exception. The emptiness is the rule. At the edges of the great nothing, the universe builds roads. Cosmic filaments, long, thin threads of dark matter and gas and galaxies, stretching for hundreds of millions of light years, run along the boundaries of the Boötes Void. They are the last structures before the emptiness begins, the final outposts, and they are busy. Matter that finds itself at the void's edge, baryonic matter, which is the ordinary kind, made of protons and neutrons and electrons, the stuff of stars and planets, and everything we can touch, tend to fall along these filaments toward denser regions. The filaments act as channels, pipes, evacuation routes for any gas or galaxy that drifted too close to the nothing. Over billions of years, these filaments have carried material away from the void's interior, enriching the surrounding superclusters and sharpening the boundary. They are the coastline of the great nothing, the place where the dark sea meets the bright land. The Boötes Void is a museum of the early universe. In denser regions of space, the violence of cosmic history has overwritten the early record. Galaxies have merged, gas has been heated and expelled, gravitational interactions have stirred and scrambled the original arrangement of matter. Reading the early universe from the dense regions is like trying to read a manuscript that has been written over many times. The original text is still there, somewhere, but obscured. Inside the void, the original text is still largely visible. The subtle density contrasts imprinted by quantum fluctuations in the first fractions of a second after the Big Bang. Those tiny, ancient cosmic whispers have been preserved here, deep in the nothing, where little has happened to disturb them. The void has been quiet for billions of years. In that quietness, it has kept a record. Astronomers studying the void's inner structure are, in a very real sense, reading a message from the beginning of time. The Boötes Void was not born this large. In the beginning, it was smaller. Many smaller voids, modest underdensities scattered to the young universe, existed in the region that will become the great nothing. Over billions of years, as the surrounding matter drained away, as the walls grew denser and the interiors grew emptier, these smaller voids merged. The boundaries between adjacent voids dissolved. One empty space flowed into another. What had been many small nothings became one enormous nothing. This process of void merging is predicted by the lambda CDM model, the current best model of cosmic structure formation. Lambda refers to dark energy. CDM stands for cold dark matter. Together, they describe a universe that forms structure hierarchically, from small to large, from simple complex, and that includes the emptiness as much as the fullness. The great nothing grew from many small nothings, gathered, merged, and became something greater than itself. Perhaps that is true of quiet things everywhere, a question that sometimes surfaces very gently in the minds of people encountering the Boötes Void for the first time. Could it be a black hole? The answer is no, and the reason why is itself illuminating. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape. It forms from extreme concentrations of mass, collapse to extraordinary density. It is defined by presence. The presence of a gravitational singularity, the presence of an event horizon, the overwhelming presence of something. The Boötes Void is defined by absence. It contains no extreme concentration of mass. It contains, as we've noted, approximately 60 galaxies distributed sparsely across an enormous volume. There is no event horizon. Light crosses it freely. Astronomers detect the galaxies within it with ordinary optical telescopes. The void is not a hole in space. It is a space that simply chose, over billions of years, to be nearly empty, and that in its own way is stranger and more beautiful. Is the Boötes Void real? That is it genuinely a physical structure, or is it an illusion created by the limited way we sample the sky? It is a fair question. Any survey of a universe is necessarily incomplete. We look out from a single point, our solar system, our galaxy, and we observe in certain directions more deeply than others. We may have missed galaxies at the void's edges or misidentified its boundaries because of the limitations of 1980 survey technology. Some astronomers have wondered whether the void, seen through a wider or deeper survey, would seem less extreme, whether the emptiness would prove less complete, the boundaries less sharp. But the size of the structure argues strongly against this being a measurement artifact. A random fluctuation in sampling does not typically produce a clean, roughly spherical emptiness 330 million light-years across. The probability of such an underdensity arising by chance in standard cosmological models is extraordinarily small. The void is most likely real, most likely physical, most likely exactly as empty as it appears. 1 in a billion. Let that number settle softly as you breathe. If you took the observable universe and randomly arranged its matter, following the statistical rules of standard cosmology, and then asked how often you would naturally produce a void as empty and as large as the Boötes Void, the answer would be less than once per billion realizations. 1 in a billion. This makes the Boötes Void what scientists sometimes call an outlier, a rarity, an event that standard models predict should essentially never happen. And yet here it is, 700 million light-years away, undeniably present. This does not mean standard cosmology is wrong. 1 in a billion events do occasionally occur in a universe as large and old as ours. We may simply be living in a time and place where we happen to observe one, but it raises questions, quiet, interesting, unsettled questions about whether the models fully capture reality. And those questions make the void more interesting, not less. The great nothing may be telling us something we have not yet learned to hear. In the first tiny fractions of a second after the Big Bang, the universe was not perfectly smooth. At the quantum level, at scale so small they are almost incomprehensibly tiny, there were fluctuations, random variations in energy density, places where, by pure quantum chance, the energy was slightly higher and places were slightly lower. These fluctuations were inflated, stretched to enormous scales during a period of rapid cosmic expansion called inflation. What had been quantum ripples became the seeds of cosmic structure. In most places, these seeds were modest. They grew into galaxy clusters and filaments and voids of typical size. But occasionally, very rarely, a fluctuation might have been unusually deep, an underdensity of exceptional magnitude, encoded into the fabric of space before a single atom had formed. The Boötes Void may be the grown remnant of such a fluctuation, an ancient quantum whisper, amplified over 14 billion years, into the largest empty space we know. The nothing may have been written into the universe before the universe had a chance to fill itself in. Cosmologists build universes on computers, not real universes, but models. Simulations that begin with a set of initial conditions and let gravity, dark energy, and the other forces of nature run forward through simulated billions of years. These embody simulations track millions or billions of particles, watching them cluster and stream and form the structures we observe in the real cosmos. When researchers try to reproduce the Boötes Void in these simulations, they find it is possible, under the right initial conditions. A void of its size and emptiness does emerge, but those initial conditions are specific. The power spectrum of primordial fluctuations, the statistical description of the early universe's density ripples, must be set just so. Too much small-scale power, and the void fills up with galaxies. Too little large-scale power, and it fails to reach its observed size. The Boötes Void sits at a precise, narrow intersection of initial conditions. It is reproducible, but only barely, only with the right seed. The universe, it seems, was holding its breath for this particular void. Even with the correct initial conditions, the Boötes Void is difficult to simulate. The challenge is resolution. Computational resources are finite. A simulation that models the entire observable universe cannot simultaneously track the fine-scale physics of individual galaxies forming inside a supervoid. You must choose broad view or fine detail. Simulating the Boötes Void properly, capturing both its vast emptiness and the detailed dynamics of its small interior population of dwarf galaxies, requires unusually high resolution, more particles, more computational steps, more memory, more time. This is not just a practical inconvenience. It reflects something real about the void's nature. It is an outlier in scale and in detail simultaneously. Its vast emptiness cannot be understood separately from the small, faint galaxies that persist within it. The void demands attention at two scales at once. The very large and the very small, held in the same field of view. Perhaps that is one of its lessons. Some things can only be understood if you are willing to look at the whole and the detail together, without collapsing one into the other. Lambda CDM is the current best story we have of the universe. It is a model built from two pillars. Lambda, representing dark energy, the mysterious force accelerating cosmic expansion, and CDM, cold dark matter, the invisible scaffolding around which ordinary matter clusters. Together, they describe a universe that matches observations with extraordinary accuracy across a wide range of scales and epochs. But the Boötes Void strains the story. It's measured under density, roughly 97% below what you expect in an average region of space, is at the very edge of what Lambda CDM predicts should be possible. Not impossible within the model, but deeply improbable, an outlier that the model can accommodate only barely, like a story that technically permits an event while clearly not expecting it. The void is not a refutation of Lambda CDM, but it is a challenge, a test, a place where the model is asked to stretch itself, to explain an extreme case where the same rules applies everywhere else. Science lives at these edges, in the places where the story almost breaks. Not everyone is satisfied with the standard story. Modified Newtonian dynamics, MOND, is an alternative to standard gravity, proposed in the 1980s. Instead of invoking dark matter to explain the rotation of galaxies, MOND suggests that the law of gravity itself behaves differently at very low accelerations, a tweak to the fundamental rule, rather than an invisible addition to the mass. MOND has had successes and failures in explaining different observations. It remains a minority view among cosmologists, but it has never been entirely dismissed. Interestingly, some formulations of MOND can predict the existence of very large voids, structures like the Boötes Void, more naturally than standard Lambda CDM, without requiring the model to reach for extreme initial conditions. Whether this is a genuine advantage or a coincidence is still debated. But the void serves as a test, a benchmark, a place where different theories of gravity make different predictions, and where careful observation can, in principle, help distinguish between them. The great nothing is a laboratory, one of the largest and most unusual in the cosmos. What if dark energy is not the same everywhere? The standard model treats dark energy as a cosmological constant, identical in every cubic centimeter of space, unchanging over time, perfectly uniform. It is an elegant assumption, simple, and it fits most observations well. But some theorists have proposed alternatives, models in which dark energy varies from place to place or from time to time. In these models, some regions of space might have slightly more dark energy, driving expansion faster than average. Other regions might have less. If dark energy is slightly enhanced inside a region like the Boötes Void, elevated beyond the cosmic average, that enhancement would drive expansion more aggressively. Matter would be swept outward faster. The interior would clear more completely. The emptiness would become more extreme. The Boötes Void, under this interpretation, might be a signature of a dark energy fluctuation, a pocket of the universe where the cosmic expulsion force was unusually strong. The nothing shaped by a local excess of the force that pushes everything apart. The universe does not expand uniformly. In the popular imagination, cosmic expansion is often pictured as everything moving evenly apart, like dots on a stretching rubber sheet, all separating at the same rate. And on the very largest scales, averaged over the whole observable universe, that picture is approximately true. But zoom in, cosmically speaking, and the picture is more nuanced. Void interiors expand faster than average. The regions inside underdense spaces like the Boötes Void are growing at rates perhaps 20 to 50% above the cosmic mean. Meanwhile, dense regions, galaxy clusters, filaments are expanding slower or even contracting locally as gravity works against the expansion. The universe is stretching unevenly. It is faster in the hollows and slower in the walls. This non-uniformity has consequences. It affects how we measure the universe's expansion rate. It complicates the Hubble constant measurements. It reminds us that the cosmos is not a simple, uniform machine, but a textured, varied, endlessly complex web of competing forces. The void is both a product of this complexity and a window into it. There is a disagreement at the heart of modern cosmology. Astronomers measuring the expansion rate of the universe using nearby objects, supernovae and relatively close galaxies, for example, get a slightly different answer than astronomers measuring it using the early universe, the cosmic microwave background radiation from just after the Big Bang. This disagreement is called the Hubble tension, and it is one of the most significant unresolved problems in modern physics. The Boötes Void and structures like it may be part of the answer. If we happen to be situated in an underdense region, not as extreme as the Boötes Void, but underdense enough, the local expansion rate around us might be slightly elevated above the true cosmic average. Our nearby measurements would then give an artificially high Hubble constant, creating the appearance of a tension with early universe measurements that reflect the true average. The void, 700 million light years away, may be a clue, a pointer toward the idea that our cosmic neighborhood itself is special, and that its specialness has been quietly distorting our view of the universe. We may live inside a void, not as large or as extreme as the Boötes Void, but a void nonetheless. This idea is central to what cosmologists call the KBC void hypothesis, named after the researchers Keenan, Barger, and Cowie, who proposed it in 2013. They noticed that within a sphere of roughly 1 billion light years centered on our galaxy, the density of matter seems to be lower than the cosmic average. Not dramatically so, not nearly as empty as the Boötes Void, but measurably underdense, a gentle hollow in the large-scale structure of the local universe. If we are inside such a hollow, then the expansion rate measured locally from our position in a slightly underdense region would naturally be slightly elevated compared to the cosmic average. Dark energy would face less local resistance. Space here would be stretching a bit faster than elsewhere. This could explain the Hubble tension. It would mean the tension is not a failure of our physics, but a consequence of our location. We are, perhaps, inside a small, quiet nothing, looking out at the universe from its slightly emptier floor. To understand the whole, you must compare the extremes. Dark energy drives expansion. Gravity drives contraction. These two forces are in constant, enormous cosmic tension, playing out across every scale of the universe, from galactic clusters to vast supervoids. By studying both extremes simultaneously, the Boötes Void expanding faster than average, and nearby superclusters contracting or at least resisting expansion, cosmologists can calibrate their models of dark energy. The void expands. The wall contracts. The difference between those rates contains information, precise, measurable information about the ratio of dark energy to gravity, about the universe's equation of state, about the nature of the force driving all of this apart. The Boötes Void is thus not merely an empty space. It is a calibration instrument, one of the universe's own mechanisms for measuring itself. When we study the void alongside its dense neighbors, we are watching the cosmos weigh itself. Baryon acoustic oscillations are one of cosmology's most elegant tools. In the very early universe, in the first few 100,000 years after the Big Bang, the cosmos was a hot, dense plasma. Sound waves propagated through this plasma, rippling outward from concentrations of matter, compressing and rarefying the gas rhythmically. When the universe cooled enough for neutral atoms to form, those sound waves froze. Their imprint, a characteristic scale of clustering, a preferred separation distance between galaxy pairs, was locked into the large-scale structure of the universe. It is still visible today as a subtle statistical signal in galaxy surveys. This frozen sound wave scale acts as a standard ruler. By measuring how large it appears at different distances, cosmologists can map the expansion history of the universe. The Boötes Void region, with its sparse foregrounds, provides an unusually clean environment for such measurements. fewer interfering galaxies between us and the signal, less contamination, a clearer view of the acoustic ruler. The nothing helps us measure the something more precisely. The cosmic microwave background is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, and the previously opaque plasma became transparent. The light that had been trapped, scattered endlessly in the dense hot gas, was suddenly free to travel. It has been traveling ever since. Today, that light fills the entire sky. It is the faint, cold afterglow of the Big Bang. Its temperature variations, the tiny hot and cold spots mapped by satellites like Planck and WMAP, contain an extraordinary wealth of information about the early universe. Studying this light requires a clear view. Foreground sources, galaxies, gas, dust between us and CMB, contaminate the signal, adding noise. In the direction of the Boötes Void, the foreground is sparse. Few galaxies intervene. The CMB signal from that patch of sky is unusually clean. The void is a window, a clear patch of cosmic glass, with most of the fingerprints wiped away. When light crosses a void, something subtle happens to it. As a photon enters a gravitational potential well, a dense region with deep gravity, it gains a little energy, blue shifting slightly. As it climbs back out the other side, it loses that energy, red shifting back. In a static universe, these two effects would perfectly cancel. But the universe is expanding. By the time the photon climbs back out of the potential well, the well has become shallower. The surrounding structure has grown slightly less dense as the universe expanded. The photon therefore loses slightly less energy climbing out than it gained falling in. The net effect is a slight blue shift, a slightly warmer spot in the CMB. For voids, the logic reverses. Photons crossing an underdense region lose energy entering and gain less back exiting. Because the void has grown deeper during the crossing, the net effect is a slight redshift, a slightly colder spot. This is called the integrated Sachs-Wolf effect, and the direction of the Boötes Void may carry exactly such a cold spot signal in the CMB, a faint, ancient thermal shadow of the great nothing, imprinted on the oldest light in the universe. Dark matter bends light, not dramatically, but measurably. When light from a distant galaxy passes through a region containing dark matter, the invisible mass deflects the light path slightly, distorting the shape of the galaxy image we see. This effect, gravitational lensing, has become one of the most powerful tools in modern cosmology. In the weak regime, small distortions distribute statistically across millions of galaxy images. It can be used to map the dark matter distribution of entire structures, galaxy clusters, filaments, and even voids. Studying the Boötes Void through weak lensing is challenging. The dark matter signal from an underdense region is a deficit, slightly less lensing distortion than average, rather than more. Detecting this subtle absence requires extremely precise measurements of extremely faint galaxy shapes across an enormous patch of sky. Current telescopes are at the edge of what is required. Future instruments, larger mirrors, more sensitive detectors, longer observation times, may be able to reveal the dark matter profile of the void, its invisible skeleton outlined by the absence of lensing, the shadow of the nothing cast in bent light. At the edges of the void, gases warm. As matter flows outward from the void's interior toward the surrounding walls and filaments, it encounters other gas. Streams of material merge. Flows collide gently at the boundary. This gentle compression and mixing can heat gas to temperatures of millions of degrees, hot enough to emit X-rays. This warm-hot intergalactic medium, as it is known, is particularly interesting at void outskirts. Here, the flows are relatively simple. Outflowing matter from the void meeting infalling matter from the walls, with relatively few complications from galaxy mergers or strong gravitational disturbances. X-ray telescopes studying the Boötes Void's boundaries can trace these outflow dynamics directly. They can watch, in thermal emission, the drama of matter evacuating the emptiness. It is a kind of cosmic exhalation, the void breathing matter outward, warming at the edges, releasing it into the larger cosmic web, the nothing exhaling into the something. Blue light at the edge of human vision carries a story. Ultraviolet telescopes, instruments designed to detect wavelengths shorter than visible light, wavelengths that the atmosphere absorbs and that require space-based observatories, have examined the galaxies inside voids like the Boötes region, and they find youth, hot, young. Massive stars radiate intensely in the ultraviolet. They live fast and die young, burning through their hydrogen fuel in millions of years rather than billions. Their presence in a galaxy is a signature of recent star formation, new suns recently born. Void galaxies show elevated ultraviolet emission. Their ultraviolet brightness, corrected for distance, suggests that star formation has been proceeding continuously, steadily, over long periods, not in bursts triggered by galaxy collisions, but as a slow, sustained process fed by the pristine hydrogen reserves these galaxies have never had cause to exhaust. In the quiet of the void, stars have been forming for billions of years. Quietly, continuously, without interruption, new suns lighting the great nothing, one at a time. Some galaxies do not announce themselves in visible light. They are too dim, too diffuse, too far away. Their stellar population is sparse enough that even the combined light of all their stars fails to register on optical telescopes as more than a smear, if at all. But they have gas, neutral hydrogen, the most abundant element in the universe, present in vast quantities in low-density environments, emits radio waves at a very specific wavelength, 21 centimeters. This emission is detectable by radio telescopes, even when the galaxy producing it is invisible optically. HI surveys, hydrogen surveys, conducted in radio wavelengths, have peered into the region surrounding the Boötes Void and found galaxies that would otherwise be missed entirely. Dwarf galaxies, gas-rich and faint, hiding in the outskirts of the emptiness, their presence revealed only by the quiet, steady 21-centimeter radio hum of their hydrogen. There may be more galaxies in and around the void than optical surveys suggest. The truly empty may be slightly less empty, populated by faint, radio-whispering dwarfs. The nothing, once again, containing a little more than its name implies. Even in the deepest emptiness, galaxies are not entirely alone. A careful radio survey of dwarf galaxies known to exist inside the Boötes Void region found something unexpected. Many of these small, isolated systems have companions, not large neighbors, not galaxy clusters or rich groups, but small companion galaxies, satellites, associates. 29 companion galaxies were detected around 12 primary targets. Little families in the dark, small groupings of 2 or 3 systems, gravitationally bound to each other at scales far smaller than the vast emptiness surrounding them. This mirrors what we see in denser regions. Even in a galaxy cluster or a filament, small galaxies tend to have satellites. The clustering hierarchy extends downward through the scales, from superclusters to groups to pairs. The Boötes Void interrupts this hierarchy at the large scales. No clusters, no rich groups, but cannot suppress it entirely at the small scales. Even deep in the nothing, gravity still whispers between close neighbors. Even there, small associations form and persist. Tiny islands of togetherness in an enormous ocean of alone. The infrared astronomical satellite, IRAS, was launched in 1983, 2 years after Boötes Void's discovery. It surveyed the entire sky in infrared wavelengths, detecting the heat emitted by dust, coal gas, and obscured objects across the universe. In the region of the Boötes Void, IRA's data revealed something that optical surveys had missed. Galaxies obscured by their own internal dust, or simply too dim in optical light to register clearly, glowed in infrared. Their heat signatures gave them away. Warm dust heated by star formation, the glow of stellar nurseries shielded from visible inspection. These low surface brightness galaxies, detected first in infrared, added to the census of void inhabitants. They were not dramatic additions. The void remained a void, but they were a reminder that any catalog or region is only as complete as the instruments used to compile it. Every new window onto the void has revealed a little more inside it. The great nothing has been slowly, modestly, gently filling in, not with more galaxies than expected, but with more than we first saw. The Boötes Void was discovered through what astronomers call a pencil beam survey. Imagine pointing a thin, narrow tube at the sky, not a wide view, but a deep one, looking in a single direction, measuring galaxies at increasing distances along that narrow line of sight, building a picture of the universe in one dimension, depth. In the 1981 survey, multiple pencil beams were directed at different regions of the sky, and in one direction, through the constellation Boötes, the beams passed through a striking gap, a long, empty stretch where galaxies were absent. That gap became the void. But pencil beam surveys have limitations. They sample the sky in thin slices. A galaxy just slightly off the narrow beam is missed. Edge regions, where the void transitions to the surrounding wall, are sampled inadequately. Wide field surveys, covering entire swaths of sky simultaneously, are needed to fully map the void's three-dimensional shape, to find the faint galaxies at its edges, to measure how abruptly the emptiness ends and the fullness begins. The original discovery was a thin thread of light into the dark. Understanding the full void requires a wider view. Science returns to the same places with better tools. After the initial discovery in 1981, astronomers came back to the Boötes Void again and again over following years and decades. Each return brought improved instruments, better detectors, more sophisticated surveys. One significant follow-up study, led by Aldrin and colleagues, conducted a more thorough search of the void's interior. They were looking specifically for any galaxies that the original survey might have missed. Fainter objects, unusual types, galaxies at the very edge of detection. They found 53 galaxies, more than the original 60 reported. No, the numbers overlap with earlier counts, and a precise census depends on how the void's boundary is defined. What matters is that the density profile was refined. The picture became sharper. The transition from interior to wall was better mapped, and the conclusion remained unchanged. The Boötes Void is a genuine supervoid. The additional galaxies found by Aldrin's team did not fill it. They merely defined its emptiness more precisely. Better tools, same profound void. How unique is the Boötes Void? The Las Campanas Redshift Survey, completed in the 1990s using a telescope in Chile's Atacama Desert, mapped over 25,000 galaxies in the southern sky. It was at the time one of the most comprehensive surveys of the large-scale structure of the universe ever conducted. It found voids, many voids, dozens of large empty regions distributed throughout the surveyed volume, but none of them matched the Boötes Void in scale. The largest voids found in the Las Campanas survey reached perhaps 200 million light-years in diameter, substantial, but significantly smaller than the 330 million light-year expanse of the Boötes Void. This confirmation that other surveys do not casually turn up structures of this size reinforces the Boötes Void's exceptional nature. It is not the only large void in the universe, but it remains one of the largest we have found, a genuine outlier, a structure that the cosmos generated only once, or at most very rarely. In everything we have been able to survey, the largest quiet place we know, every discovery carries the fingerprints of the instrument that made it. The 1981 survey that revealed the Boötes Void was conducted with the tools available at the time, modest by modern standards. The survey's depth was limited. Its sky coverage was narrow. Its ability to detect faint galaxies at the edges of the void was imperfect. This has led some researchers to question whether the void's shape, described as roughly spherical, is a genuine physical feature or partly an artifact of the survey geometry. A deeper survey, they suggest, might find galaxies along the line of sight that the original missed, changing the void's apparent extent in that direction. A wider survey might better define the edges and plane of the sky. These are healthy scientific questions. They do not undermine the void's existence. The emptiness is too large and too well confirmed by subsequent work to be a measurement artifact. But they remind us that even our best measurements are models, approximations, dependent on the tools we use to make them. The void is real. Its exact shape is still being refined. The Boötes Void is enormous, but the universe is room for even larger structures. In recent years, astronomers have proposed the existence of structures called galaxy bubbles or megavoids, even larger under dense regions, reaching perhaps 1 billion light years in diameter. Some of these are still being investigated. Some are contested. The largest structures challenge not just models, but the very homogeneity of a universe on the scales where cosmology assumes smoothness begins. Against this backdrop, the Boötes Void at 330 million light years is not the largest possible thing. It is not the champion of all emptiness, but it remains one of the best confirmed, best studied, most precisely measured supervoids we know. Its discovery is almost 50 years old. It has been scrutinized by dozens of surveys. It has survived the test of improving instruments. In the catalog of cosmic voids, it sits near the top. Thoroughly real, exceptionally empty, scientifically extraordinary, not the largest. Simply one of the clearest examples of what the universe can make when it chooses to make nothing. The void teaches a lesson about organization. Matter in the universe is not randomly distributed. It has been sorted by gravity, by dark energy, over billions of years, into a hierarchy of structures, filaments, sheets, walls, and superclusters, all connected in the three-dimensional lattice called the cosmic web. And the cosmic web is largely hollow. The filaments are thin. The walls are relatively flat. The clusters are compact. All of these high-density structures, all of the something in the universe, occupy only about 20% of the total volume. The rest is voids. The Boötes Void exemplifies this beautifully in its scale. It is the emptiness that defines the fullness. Its existence is what makes the surrounding superclusters visible as structures at all. The contrast, the boundary, the edge between nothing and something. Without voids, there would be no filaments. Without empty space, there would be no defined walls. The structure of the universe requires its emptiness as much as it requires its mass. The nothing holds the something together. Ordinary matter, the kind made of protons and neutrons, the kind that makes up stars and planets in us, follows dark matter. This is one of the foundational insights of modern cosmology. Dark matter, which constitutes about 27% of the universe's total energy content, forms the gravitational scaffolding. Ordinary matter, comprising only about 5%, falls into the wells that dark matter creates. In dense regions, this relationship is complicated. Ordinary matter forms galaxies, which interact, which heat gas, which drive feedback processes, all of which complicate the simple dark matter baryons relationship. In the Boötes Void, things are simpler The ordinary matter that exists inside the void occupies exactly the regions where dark matter concentrations are highest. Even if those concentrations are themselves thin, the tubular arrangement of galaxies through the void's center reflects the thread of dark matter running through it. By studying where the galaxies are in the void, astronomers can trace the invisible skeleton they are sitting on. The void is a place where the ordinary and the invisible are close enough in simplicity to be compared. A map of the visible becomes a map of the unseen. The universe is testable. This is one of the most important things about it. Not merely describable, not merely beautiful, but testable, subject to prediction, open to being proved right or wrong. Lambda CDM makes specific predictions about the universe's large-scale structure. It predicts the distribution of voids, their sizes, their shapes, their depth, their growth over time. It predicts how many voids of a given size should exist in a given volume, and how that number has changed from the early universe to present. The Boötes Void is a test of these predictions. Its size, its emptiness, its age, its location relative to surrounding superclusters. All of these are quantities that Lambda CDM either accommodates or struggles to accommodate. By measuring them precisely and comparing predictions, cosmologists can evaluate how well the standard model holds up at its extremes. So far, the model survives, barely, with some strain, but the test continues. Future surveys will map the void more completely. Future simulations will resolve it more precisely. The void will keep asking its question, and cosmology will keep trying to answer. The universe's expansion rate is a number with a problem. The Hubble constant, the rate at which the universe expands, measuring kilometers per second per megaparsec, has two main observational values, and they disagree. Measurements based on the early universe give a lower value. Measurements based on nearby objects give a higher value. The gap between them is small in absolute terms, but in the language of cosmological precision, it is significant. It is called the Hubble tension. The Boötes Void, along with other large-scale voids, is one of the proposed contributors to this tension. If we measure the expansion rate using nearby galaxies in the direction of under-dense regions, regions where dark energy drives expansion faster than average, we get an inflated local rate. The void's faster expansion contaminates our measurement of the global Hubble constant. By carefully mapping which lines of sight pass through underdense regions and which pass through dense filaments, cosmologists hope to untangle the local measurement bias from the true cosmic expansion. The void is part of the puzzle, perhaps even part of the answer. At the very beginning, in the first trillionth of a trillionth of a second, the universe underwent a period of extraordinary, accelerating expansion called inflation. In this blink of cosmic time, space expanded faster than light. The tiny quantum world was stretched to astronomical scales. Microscopic fluctuations, the random noise of quantum physics, were inflated into wrinkles on the fabric of the cosmos. These wrinkles were the seeds of everything. Most seeds grew into galaxies and clusters and filaments, but some seeds were under densities, places where quantum foam happened to be slightly sparser than average. These underdensities were also inflated. They were also stretched across billions of light years. The Boötes Void may be the grown form of such a seed, an ancient quantum fluctuation, a momentary thinning of the early universe's energy, stretched across 330 million light years of modern space, amplified by 14 billion years of cosmic expansion into the largest known emptiness. The nothing we see today may have been written into existence before the universe was a second old. There is more to learn. The European Space Agency's Euclid mission, launched in 2023, is a wide-field space telescope designed to map the geometry of the universe with unprecedented precision. Over its mission lifetime, it will survey billions of galaxies across enormous volumes of space, creating the most detailed three-dimensional map of the cosmos ever assembled. One of Euclid's primary science goals is precisely the kind of question that the Boötes Void raises. How does dark energy shape large-scale structure? With Euclid data, astronomers will be able to map the Boötes Void's edges with far greater completeness than current surveys allow. The faint galaxies at its boundaries, those barely detected in today's observations, will be cataloged with precision. The void's true three-dimensional shape will be revealed. And with that shape, the signature of dark energy's influence will become clearer. The expansion rate of the void's interior, compared to contraction or slowing of its surrounding walls, will be measurable with new accuracy. The great nothing will be better understood. Slowly, carefully, with patience. The boundary of a void is not a clean line. In reality, in the three-dimensional continuous universe, the transition from void interior to surrounding wall is a gradient. The density rises slowly at first, then more steeply as you approach the walls. Along the way, there may be thin, faint structures, protofilaments, partial sheets, wisps of matter that are dense in the void but far less dense in the walls. These edge structures are difficult to detect with current surveys. They are too faint, too extended, too subtle. Euclid's wide-field imaging and spectroscopy may be sensitive enough to find them, to trace the gentle density gradient at the Boötes Void's edge, to identify faint filamentary structures threading through the boundary region, channels through which matter flows slowly from the interior toward the walls. Finding these structures will refine our models of how voids evolve, how matter drains, how boundaries sharpen over cosmic time. The edge of the nothing may be more structured than it appears, and understanding that structure will tell us something about how the nothing came to be. Looking through the void is like looking through very clean glass. When astronomers study the large-scale structure of the universe, the distribution of galaxies, the shape of the cosmic web, the statistical patterns encoded in billions of galaxy positions, they must contend with foreground contamination. Every galaxy between the observer and the target contributes light, confusion, and systematic errors. In most directions, this foreground is substantial. The Milky Way's own disk is full of stars and dust. Intermediate galaxy clusters add their light. Nearby foreground galaxies overlap with more distant targets. In the direction of the Boötes Void, the foreground is thin, fewer galaxies intervene. Less dust, less confusion, less contamination. This makes the void direction one of the cleaner lines of sight available to large-scale structure surveys. Background galaxies, used to study lensing, to map the cosmic web at great distances, to measure baryon acoustic oscillations, can be observed with less systematic uncertainty. The emptiness of the void is not merely an object of study. It is a tool, a window through which the deeper universe can be seen more clearly. The nothing serves the science. You cannot see the Boötes Void, not with your eyes, not with a backyard telescope, not even with a modest professional instrument, pointed at the right patch of sky. This is not because it is too faint. Faint things can be detected by large telescopes. This is because it is not a thing. It is an absence, and absences do not have a brightness to measure. To see the Boötes Void, you must build a map, a three-dimensional map of galaxy positions, assembled from thousands or millions of individual redshift measurements. And then you must look for where the dots are not. This is science at a scale that has no parallel in human scale experience. It requires coordinated observations by multiple telescopes over years or decades. It requires algorithms to process millions of spectra. It requires the collaborative effort of hundreds of researchers. All of that work to confirm the existence of something that contains almost nothing. The void is invisible, and yet it is one of the most clearly defined structures in the observable universe. It takes a civilization to see nothing. We have spent a long time tonight in the nothing, drifting through a space 330 million light years wide, exploring the 60 galaxies that make their quiet homes there, tracing the dark matter skeleton, listening to the slow expansion, following the faint thread of the central filament. And what the Boötes Void teaches, if it teaches anything at all, is this: absence is not nothing. The void shapes the universe as surely as the galaxies do. Its expansion drives the cosmic web to grow. Its emptiness defines the walls and filaments by contrast. Its spare interior preserves records of the early universe that the dense, violent regions have overwritten. Its faint galaxies show us star formation undisturbed by billions of years of cosmic drama. The nothing has a structure. The nothing has a history. The nothing has a future. In a culture that values density, of information, of experience, of stimulation, the Boötes Void is a quiet argument for the value of emptiness, for the information contained in silence, for the structure revealed by the absence of clutter. Some of the most important truths live in the spaces between things. And now, one last thought, the most speculative, the most gently improbable. For some researchers and thinkers who find themselves captivated by the Boötes Void, its extreme emptiness raises a question that science cannot currently answer, and perhaps never will. What if it is not entirely natural? The idea is this: a sufficiently advanced civilization, one millions or billions of years ahead of our own, might, in principle, possess the ability to manipulate the physical environment of a region of space, to concentrate resources, to rearrange matter, to perhaps clear a region of normal density matter for purposes we cannot imagine. The Boötes Void's extreme underdensity, the 1 in a billion improbability of its existence under standard models, is, to some imagination, suggestive. There is no evidence for this. None. It remains a thought experiment, a piece of speculative cosmology, an invitation to wonder. But there is something beautiful in the idea that the largest empty space we know might be a garden, a clearing, a deliberate silence in the cosmic conversation, a great nothing made meaningful. Let that thought drift slowly away, into the dark, into the quiet. You do not need to hold it. We have arrived together at the far side of the nothing. We have crossed 330 million light years in thought. We have visited 60 galaxies in their solitude. We have watched dark energy expand the void. We have felt the cold whisper of ancient quantum fluctuations. We have listened to blue stars forming in the silence. And now, it is time to let all of that go, to allow the facts to dissolve, like salt in warm water, to let the void become simply stillness. You are here, in your room, in your body, which is warm and breathing and entirely safe. The universe will continue its slow work without you tonight. The void will expand its quiet millimeters. The 60 galaxies will continue their patient rotations. The dark energy will push, unhurried, in all directions at once. You do not need to watch. You can let your eyes rest, your thoughts slow, your breath deepen. Somewhere 700 million light years away, a small blue dwarf galaxy is making a new star tonight. Quietly, without announcement, without audience. And you, in your small warm room, in your small warm life, on your small warm planet, are part of the same universe that made that star, part of the same fabric, the same deep, patient, unimaginably vast whole. Sleep well. The nothing holds you.